Good day friends, let's begin with our second lecture on unit number 2. We'll start with petrology. So petrology is branch of geology that studies rock and conditions under which they are structured, their occurrence and their distribution, their origin in relation to physiochemical conditions and geological processes. It is concerned with all three major types of rocks, that is igneous forms. So petrology is the scientific study of rock that is with under composition, texture and metamorphic and sedimentary rocks. The field of petrology is traditionally classified into three subcategories: igneous, metamorphic and sedimentary petrology. So igneous petrology is concerned with the identification, classification, origin, evolution and processes of formation and crystallization of the igneous rocks. Most of the rocks available for the study come from the earth crust, but a few such as eclosites derive from the mantle. The scope of igneous petrology is very large because igneous rocks make up the bulk of the continental and oceanic crust and of the mountain belts of the world. Igneous rocks are formed from magma. Magma is a molten state below the earth. So igneous rocks are divided into general categories of plutonic, hyperbasal and volcanic rocks depending on their occurrences. So igneous rocks are divided into general three categories: plutonic, hyperbasal and volcanic rocks depending on their grain size. So plutonic rocks, their characteristics have coarse or medium grain size greater than 1 mm and are inferred to have crystallized deep in the crust. Hyperbasal and volcanic rocks are fine grained to glassy. Volcanic rocks are crystalline at the surface and hyperbasal rocks crystallize at a low depth, typically less than a kilometer. Because the grain size of an igneous rock is determined in part of by the cooling rate of the magma, and this is a function of both of magma temperature and the ambient temperature of the rocks into which the magma was influenced. Grain size generally increases with depth, but there is no specific depth associated with the transition from plutonic to hyperbasal rocks. In addition to classification according to grain size, the general composition of a rock can be described using the term felsic, mafic, and ultramafic. Rocks like rich in quartz, feldspar, or feldspathoids are light colored and are called felsic. The term felsic combines parts of the words feldspars and felspathoids and silica. Darker colored rocks uh, rich in ferromagnesium minerals are called mafic. The term mafic reflects the enrichment of these rocks in the magnesium and iron, that is ferrous or Fe. Ultrafilmic rocks are essentially free of any felsic minerals. Now, texture is defined on the basis of glass versus mineral grain proportions, their sizes, shapes, and mutual alignments. Perhaps you may have questions asking about importance of texture and structural studies. Thus, the textures help us to identify different rock types. The term texture is applied to microscopic as well as observed in hand specimens with unaided eyes, as well as microscopic features as observed in the thin section under the microscope. Following textural elements with reference to igneous rocks are crystallinity, degree of crystallization, granularity, grain size, shape of the mineral grains, and mutual relationship among crystals and glass as well. Crystallinity. Crystallinity or degree of crystallization refers to degree of amounts of crystals formed during the process of solidification of magma. The igneous rocks may be composed of the crystals, and partly glassy matters, or totally glassy glassy matter. Degree of crystallization is measured by the ratio between the crystallized matter and the glass in an igneous rock. It is the model percentage of mineral grains relative to glass and varies between 0 to 100%. Granularity. We have already discussed about crystallarity, but now let us introduce you to few important technical terms related to granularity. Grain size or granularity of igneous rocks show wide variation. It varies from a meter size, that is pegmatite, to a few centimeters, or to even to less than or equal to 0.01 millimeter size of microlith, or sometimes even glassy, as found in volcanic rocks. General phenolitic and aphanitic terms are used to describe coarse and fine-grained rocks, respectively. Coarse-grained crystals can be seen with unaided eyes, and the mineral grains in rocks are identified easily. Whereas the study of fine-grained minerals in rocks requires petrological microscope for their identification. Synonym terms for aphanitic texture are hyaline or glassy texture. The alternative terms used for phenolitic and aphanitic rocks are pyritic and apyritic respectively. Shape of crystal. The three important terms euhedral, subhedral and anhedral, and their resulting textures that are universally used to describe the relative proportion of the grain size. Euhedral term. First one, euhedral term used for mineral grains which possess fully developed grain or crystal outlines. All the faces are perfectly or near perfectly developed. Idiomorphic and automorphic are equivalent terms used for euhedral grains. Panidomorphic granular texture, that is panel idea one's own morphous shape, comprises majority of grains with euhedral shape. Example of this rock is pegmatite. Now second term, subhedral, refers to crystal forms with less or partly developed crystal faces or grain boundaries. Hypodomorphic granular textures that hypoless or below consist of dominantly of mineral grains with partly developed or subhedral shape. For example, gabbro and granite. Thus, hypodomorphic granular texture is the commonest of the granular texture, also called granitic, because this is mostly found in granite. Third one, anhedral term is used for mineral grains lacking crystal outlines. When majority of the grains are anhedral, resulting texture is known as allotriomorphic granular texture, allotriolane, also called as xenomorphic granular texture. Example of this applied. This texture is also called as apletic because this is best developed in applies. That is hyperbosal equivalent of granite. Now granites may be defined as plutonic light colored igneous rocks. Two most common and essential mineral constituents of granite are quartz and feldspar. Among other accessory minerals found in granites may be mentioned magnetite, oxide of iron, apatite, garnet, and tourmaline. Granites find extensive use in architecture and massive construction where they are found in abundance. These rocks have been used extensively in monuments and memorials as columns and steps and as floorings in buildings. Diorite. It is an intermediate type of igneous rocks of plutonic origin with silica percentage generally lying between 52 to 66%. Diorites are typically rich in feldspar, plagioclase of sodic group. For example, albite. Beside plagioclase and alkali feldspar, diorites also contain accessory minerals like hornblende, biotite, and some pyroxenes. Quartz is not common but may be present in some varieties. Now textures of sedimentary rocks. So sedimentary rocks may have clastic, that is fragmental texture. Grains are stuck together. Characteristic of plastic sedimentary rocks. Example sandstone and conglomerate. Non-plastic, that is crystalline texture. They have interlocking crystals. Characteristics of chemical sedimentary rock. Example limestone, dolomite and jade. Maturity depends on how many cycles of erosion and redeposition the components of the rock have undergone. There are two types of maturities. Compositional maturity is equal to quartz plus chase or feldspar plus rock fragments. Textural maturity, sorting and roundness of this sand size grains. Color, organic matters, sulficides and some iron oxides give dark rocks a dark color, indicating deposition in a reducing environment. Some iron oxides give rocks red or yellowish color, indicating deposition in an oxidizing environment. Color indication, black organic matters, ferrous sulfide, yellowish pyrite marcasite, ferrous disulfide, yellowish or bluish sulfates, carbonates and chlorides, yellowish to brownish limonite, goethite or ferrous hydroxide, reddish iron oxides or ferrous oxides. Cohesiveness, that is firmness, the degree to which the particles stick together. Cohesiveness can be described as fragile, soft, intermediate, hard, and very hard. Mineral composition. The most common minerals in sedimentary rocks are quartz, then clay minerals, feldspar, carbonates, calcite and dolomite, rock fragments, small amounts of amphibole, pyroxene and mica. Sedimentary structures. Some common sedimentary structures include bedding, that is stratification, lamination, then graded bedding, cross bedding, ripple marks, mud cracks, raindrop impressions, nodules, concretions, geodes, and stromatolites. Stromatolites. Framework and matrix. The grains in a sand size or coarse grain sedimentary rocks are known as framework. These grains are either in contact with each other, surrounded by empty spaces, that is pore spaces, surrounded by final grain sediments, that is matrix, cemented together by bonding material, that is cement. These are the typical sketches of the framework and matrix. This is grain with intergranular pore spaces. This core grains with final grain matrix. Then grains bounded together by chemical precipitated cement. So you can see it here in the figure shown here. Common type of sedimentary rocks are laterite. It is a reddish withering product of basalt. At least this is what it is in India, where this rock or a soil used as a building stone and for decorative purposes. Now, metamorphism, process of mineralogical and structural textural changes of rocks in solid state in response to physical and chemical conditions which differ from those under which they are originated. So mineral assemblages change to textural changes, that is pollution, cleavages, etc. Physical condition equal pressure and temperature, chemical condition pH2O, PCO2, fluid solutions, water dissolved solids, all metamorphic rocks, whether ones igneous or sedimentary. Lower and upper limits of metamorphism. Low grade diagnosis, incipients, metamorphism 100 to 150 degrees Celsius. High grade annexitous, formation of partial melt 750 degrees to 850 degrees Celsius. Pressure variation. Top of the crust 1 to 3 km. Pressure less than 1 kilo. Right. Base of crust 20 to 40 km greater than 10 kilo. Factors of metamorphism. Temperature 100 to 50 degrees Celsius. Confining pressure or lithostatic pressure, that is synonymous term. Equal weights of overlying rocks column, same pressure on all sides. Goal of metamorphic petrology. Setting. Where did metamorphism occur? What was its structure and tectonic setting? Protolith. Original nature of the rock before metamorphism. Grade of metamorphism. How intense was the metamorphism? What were the physical and chemical conditions of the metamorphism? A look for relic structures fossils. D. Look at mineral assembling and compare to experimental studies in mineral equilibrium. Estimate temperature and pressure. C. Calculate using mineral composition. Example: garnet, biotite, geothermometer. Thank you.